All right, we are in section 4.3, area and definite integrals. And as you can see from our objectives here, we're going to find the area under the graph of a non-negative function over a given closed interval. We're going to evaluate a definite integral, and we're going to solve some applied problems involving definite integrals. The vocabulary, probably the most important vocabulary piece that we're going to have throughout the course, is the fundamental theorem of calculus. With a name like that, you would expect that to be pretty important, and it is. It's what actually is going to link the differential calculus with the integral calculus in areas under the curve. So we're going to start to see how it all connects now. Okay, so let's go ahead and take a look at what this fundamental theorem of calculus is. A lot of times we just abbreviate that FTC in order not to have to write it all out every single time. And specifically, there are actually two parts to the fundamental theorem of calculus. This is actually what's considered part two. It's the more important one that we are going to use in this class. It's the one that pretty much is going to define how we're actually going to take integrals from here on out. It says, if a continuous function f of x has an antiderivative, capital F of x, on the closed interval from a to b, such that if I were to take the derivative of that capital F of x, it gives us the lowercase f of x, so there's your connection with the derivatives. Then what we can say is the integral from a to b, so between my two endpoints, of f of x dx is going to be capital F of x, or just the antiderivative, and then this little piece right here, I tend to write it in a slightly different fashion, and you'll see it when we go to it, but this piece right here, it just says we're going to evaluate that antiderivative at b and at a. And what you can see is you take the upper bound, b, you plug that in first, then you take the lower bound, a, and then you plug that in, and then you subtract them. And so the notation, this f of x, this capital F of x, with the b and the a, again, I tend to write that slightly differently. I write more of an elongated bar right here, and a and b at it. Again, you'll see it when we get to it. This is going to be useful in evaluating definite integrals using the fundamental theorem of calculus. So it seems simple. It's really not that difficult of a concept. There's a lot more that goes into actually why all this stuff works, and we won't get into the heavy mathematics there, but we will at least show the algebraic mathematics as to why it works. What's really nice about this, though, is we no longer need to use Riemann sums. We don't need to approximate this with, like it says here, curves using 100 rectangles or something like that. If we can just find the antiderivative of the function, then we can get the exact area under the curve just by evaluating a simple function. So not really the most challenging things. Now, the biggest thing is if. It says if we can get the antiderivative. There are functions in which you sometimes cannot take the antiderivative of, or at least not easily, and we will learn some techniques for that. Some things we will not get into in this class as far as how to do, but there are definitely several functions you just can't take an antiderivative easily of or at all. So there are other methods that we won't get into, but for the most part we'll be able to do it in some fashion. Okay, so let's see that this actually works. Let's check that this definite integral from example 5 at the end of the previous section, the integral from 0 to 2 of 3x plus 2 dx. Remember, I did tell you there would be an algebraic way to solve this? Well, here it is. So since f of x, or excuse me, lowercase f of x is 3x plus 2, its antiderivative is going to be capital F of x is 3/2 x squared plus 2x plus some constant c. That's the antiderivative. Well, according to this, what it says is if I want to take this integral, I find the antiderivative and I evaluated it 2 and I evaluated it 0 and I subtract them, and that's because 0 and 2 are the bounds. You always evaluate it upper bound minus lower bound. Okay, so then we're going to take, and again, I write this slightly differently, but I would put an elongated bar here instead of the brackets, but it's the same thing. If you see it either way, it's going to be fine. Just means evaluate that at 2, evaluate that at 0. So you can see we've plugged in 2, we've plugged in 0 to the function, and then we're going to go ahead and subtract the results. And after some simplification, what you can see And the most important thing is, yes, you're going to evaluate all of this right here. You're going to figure out numerically what that stuff comes out to be. And obviously, all this stuff over here on the right side is going to be 0, because 0 squared times 3 halves is 0. 2 times 0 is 0. That stuff is going to go away. Doesn't always happen, but when you get zeros, a lot of times that does happen. So really all you have left is the 3 halves times 2 squared plus 2 times 2. But then you have this c minus c. And this is always going to happen in a definite integral. The c minus that c right there is going to go away every single time. So we don't even need to concern ourselves with c. Now down here in the bottom it says we're going to take c to be 0. It doesn't really make any difference. You don't even have to think about what c is. You're not even going to use c when you're doing a definite integral, because it's always going to subtract out. And then you just simplify 3 halves times 4 plus 4, and you get 10, which should have been what we came up with for the area in the last section. All right, so let's go ahead and do example 1. And we're going to find the area under the graph of y equals x squared plus 1, which is a parabola, so it's not just an easy geometric shape to do, over the interval from -1 to 2. So if we want to find the area, we simply set up an integral from -1 to 2 of x squared plus 1. And this part is extremely important. So again, notation is very important. Dx, that tells us what I am taking the integral with respect to. Technically, the dx part is really just it's the base of the rectangles. The x squared plus 1 represents the height of the rectangles. And remember that the integral symbol really means we're just adding up a whole bunch of these rectangles. Well, the integral is a way of taking the limit of an infinite number of rectangles, so it's a shorthand notation for that. So we really technically still are taking an infinite number of rectangles, but we don't have to deal with doing all the bases times heights. We're just going to do the antiderivative, and that'll take care of it. Okay, so let's go ahead and follow the procedure. It says take the antiderivative. So the antiderivative of x squared is 1/3 x cubed. Remember, raise the power by 1, divide by the new power. Dividing by 3 is the same as multiplying by 1/3. You can write it as x cubed over 3. It doesn't matter. Plus the antiderivative of 1 is x. Now here's where the notation differs. I just put one single bar from -1 to 2. Make that actually look like a -1. There we go. And now all we have to do is we have to evaluate this at 2 and at -1. So we plug 2 in first. So we get 1/3 2 cubed plus 2. Okay, that's the first one. And then we subtract, plugging in -1. When you're plugging in negative numbers, I strongly suggest you use parentheses for those, so you don't lose some part of the negative sign somewhere. And now we can evaluate. So let's see, in the first parentheses, I'm going to get 1/3 times 2 cubed. 2 cubed is 8, so that's 8/3 plus 2. We'll simplify that in a second, minus. In the second parentheses, we get 1/3 times -1 cubed. -1 cubed is -1, so that's -1/3. Plus -1 is just -1. Now, I tend to do this in a slightly different way. I'm going to combine the terms that already have common denominators first in hopes that maybe they'll become whole numbers, and in this case, it will. So I've got an 8/3 minus a -1/3, which is really plus 1/3. So 8/3 plus 1/3 is going to give you 9/3, which of course is just 3. We'll simplify that in a second. And then I'm going to do 2 minus -1, which is 2 plus 1, which is just plus 3. So ultimately, we get 3 plus 3, which is 6. And that's the area under the curve. Now, I definitely spread that out a lot longer. It usually won't take that long to be able to figure this out. Most of the mistakes that people are going to make is literally in this step right here, simplifying the just the numeric portion. Okay, let's go ahead and go on to the next page. All right, so example 2, let y equal x cubed represent the number of kilowatts generated by a new community-owned solar array each day. So that's the number of kilowatts per day. It's a rate of change, which means it is technically a derivative. X days after going online. So find the area under the graph of y equals x cubed from 0 to 5 and explain what that area represents. Okay, so the idea is we set up the integral from 0 to 5 of x cubed dx. Okay, antiderivative of x cubed is x to the fourth over 4, or the same thing as 1/4 x to the fourth. And we will evaluate that from 0 to 5. So if I plug the 5 in first, I'm going to get 1/4 5 to the fourth, minus, plugging in 0, I get 1/4 0 to the fourth. Of course, that 0 to the fourth is 0 times that 1/4. That's done. I don't need to worry about that. So all I have to do is figure out what 5 to the fourth is. That's actually 625 times 4 is just 625 over 4. 625 over 4. Now, what kind of units is this? Well, we started off with a derivative which was kilowatts per day. Okay, so the original units of this function right here, whoops, did not mean to do that. Oh, wow. Come on, there we go. Let's erase this. I'm trying to, it's not working. Whatever. Okay, something really weird is going on. All right, so I apologize about all that. That thing right there is in kilowatts per day. When I take the antiderivative of this, it now just goes back to an accumulation of the original, which was the number of kilowatts. So this is in kilowatts. And what I have done, remember that an integral says we're going to add up a bunch of things. We have just accumulated or added up the total number of kilowatts used from 0 to 5. And I don't know if this has any, oh yeah, days, from 0 to 5 days. So we've just used 625 over 4 kilowatts in that 5-day span. That's what that actually means. All right, so let's go ahead and just get some more practice in on definite integrals. We've got A through D here. All right, so the first one, x squared minus x, we're going to take the antiderivative and we're going to get 1/3 x cubed minus 1/2 x squared, and we'll evaluate that from -1 to 4. Notice when I say this, I say from -1 to 4 because technically that's left to right on the graph, and when I write it, it's bottom to top because the left is the bottom, the top is the right. If you think about that, I'm just going from the bottom or from the least to the greatest. All right, so let's go ahead and plug these things in. So we're going to get 1/3 of 4 cubed minus 1/2 4 squared. Okay, that's the first piece. Minus 1/3 of -1 cubed minus 1/2 of -1 squared. All right, so let's see what we get here. 4 cubed is 64, so that's going to be 64 thirds. 4 squared is 16, but 16 times 1/2 there is going to be 8, so minus 8. Minus, let's see, 1/3 times -1 cubed is -1/3. -1 squared is 1, so that's just going to be minus 1/2. So 64 over 3 does not divide evenly, but I do have this extra 1/3 out here that I can use. So that's going to be 64 plus 1/3, so it's 65 thirds. Still isn't going to help us out as far as that's concerned. Okay, 65 thirds, that's from the two things in green. Then I'm going to have -8 plus 1/2, which is going to be -7.5, which is the same as -15 halves. So now we're just going to have to combine these into sixths. Numbers are going to get a little big here. So let's see, in 6, the thirds is going to be 65 is going to change, multiplying both by 2. So that's 130 over 6 minus 45 over 6, it looks like. So let's see, 135 minus 45 is going to be 85 over 6. Okay, if I did that correctly, hopefully I did. You guys can double check with your calculators to make sure that that is correct. I'm pretty sure that I did okay there. We'll see if that's not right. Okay, second one. Integral of e to the x dx from 0 to 2. So the integral or the antiderivative of e to the x is just e to the x. And I'll evaluate that from 0 to 2. So we plug in 2 first and we get e squared. We plug in 0 and we get e to the 0. E squared is not something that we know easily, so we're just going to leave it like that. We're not going to use a decimal there. So it's just e squared. But e to the 0 is 1, so it's e squared minus 1. Let me make that look like a square. E squared minus 1. And that's it. That was pretty straightforward. Okay, the integral of 1 over x dx from 2 to 5. So the integral of 1 over x, remember that that's a natural log. So that's the natural log of the absolute value of x. Technically don't need the absolute value here because 2 and 5 are both positive, but we're going to leave it there just for now. So, oops, I got to put my bounds here. So that's from 2 to 5. So we'll plug in 5 first, and we get the natural log of 5 minus the natural log of 2. Now, again, I could drop the absolute value because 5 is already positive, 2 is already positive. So that is a correct answer. Nothing wrong with that. You might see it written in a different form. You might see it written as the natural log of 5 halves using properties of logs, combining those two. It's the same thing. The first one is perfectly acceptable. The second one would be a way that you might see it if it was on a multiple choice. Just know how to convert just in case you get something like that. Okay, and in part D, you'll notice again it's 1 over x, so we know we're going to get the natural log of x, absolute value of x, excuse me, from -4 to -1. Now this is the perfect example right here of why you need the absolute value, because if I drop the absolute value, I can't take the natural log of -1 or -4. But with the absolute value, this still works. So now I can do the natural log of the absolute value of -1 minus the natural log of the absolute value of -4, which is going to end up being, well, the absolute value of -1 is 1. So it's the natural log of 1 minus the natural log of the absolute value of -4, which is the natural log of 4. Don't know the natural log of 4, but the natural log of 1 is 0. So what we get is 0 minus the natural log of 4, or the negative natural log of 4. And again, this right here is a perfectly acceptable answer. You might see it written, because one of the properties is that you can bring a coefficient, that negative, up to be the power of the 4. So you could see it written as the natural log of 1/4. Be exactly the same thing. Again, that's not really what I'm looking for. If you get me to the negative natural log of 4, we're doing good. All right, real quick thought experiment here on this one. What if I was to take the integral from -3 to 3 of x cubed dx? Well, I've kind of worked it out here for you already. You would get 1/4 x to the 4th from -3 to 3. If you were to plug in the 3, and then you were to plug in the -3, you end up getting 81/4 minus 81/4, which is 0. So that's kind of a strange concept considering we're talking about area under a curve. How do I get an area under a curve that we know actually has area to be 0? What happened there? Well, we'll talk about that when we get to the next page. All right, so here you can see graphically what's going on. X cubed is that graph on the left. And remember that it's the area between the curve and the x-axis. That's important because we've always been saying the area below the curve. Technically, it's not below the curve, it's between the curve and the x-axis. So on the positive side, you can clearly see that the area right here is below the curve and between the x-axis. But on the left-hand side, between the curve and the x-axis is actually area in this blue shaded region, which I'm now striping in red, which is actually between the x-axis and the curve. It's above the curve, but that's because above the curve is between the x-axis and the curve in this case. What is actually happening is these two areas from -3 to 3 are basically canceling each other out. The area which is below the x-axis, so between the curve and the x-axis but below the x-axis, is considered to be negative area. Or at least that's what we call it. Technically, there's no such thing as negative area. But what it is, it's a net area. So the area below the curve is technically considered to be negative. The area above the curve is considered to be positive. When we add the positive and negative areas together, we get the net area of 0. So when we talk about this, again, we want to carefully describe the integral as not necessarily the area under the curve, but the net area maybe under the curve. I like to say the area between the curve and the x-axis. Again, the biggest takeaway is area below the x-axis is considered to be negative. Area above the x-axis is considered to be positive. So looking at example 4, even before we go ahead and take the integral, once we've graphed this and you can see all that blue shaded region, you should be able to kind of give me an idea of whether you think the final answer is going to be positive or negative. Well, looking at the amount of blue shaded region below the x-axis compared to the amount of shaded region above, it's pretty clear that this should be a negative overall area. It looks like there's way more blue below than there is above the x-axis. Well, now we can actually go ahead and evaluate this and figure it out. So let's figure this out. The antiderivative of negative x cubed is -1/4 x to the 4th. Antiderivative of 3x is going to be 3/2 x squared. Antiderivative of -1 is just -x. And we will evaluate that from -1 to +2. So let's go ahead and plug these values in. If I plug in 2, we get -1/4 times 2 to the 4th plus 3/2 times 2 squared minus 2. And then if we plug -1 in, we get -1/4 times -1 to the 4th plus 3/2 -1 squared. It's supposed to be a -1. Minus -1. And that right there is a perfect example where you really want to make sure you have that parentheses to make sure you don't mess up that sign. Okay, so let's go ahead now and evaluate what we've got. So 2 to the 4th power is 16, multiplied by -1/4 is -4. 2 squared is 4, multiplied by 3/2 is going to give us 12/2, which is the same as 6. And then minus 2. That first parentheses worked out pretty well. Next one's going to have some fractions left in it for sure. So -1 to the 4th is +1. So that's going to end up multiplying by the -1/4, which is -1/4. -1 squared is +1, so that's +3/2. And then minus 1 is +1. So let's go ahead and figure out what we get in the first parentheses. So the first parentheses is going to be -4 plus 6, which is +2, minus 2, which is 0. And then the second parentheses, we are going to have to do a little work. We're going to have to convert everything into fourths, it looks like. So -1/4. Changing 3/2 into fourths, we're going to get 6/4. Changing 1 into fourths, we get 4/4. So inside that parentheses, we get -1/4. So -1 plus 6 is 5, plus 4 more is 9. So we get 9/4. And 0 minus 9/4 is -9/4. So our original thought was that the area would give us a negative area, and it does. It gives us -9/4. All right, we only have one more example to do on this page, and I think we have one more on the next page. So I think I'm going to come back in a separate video to do those. Okay, I take that statement back. I literally just checked the next page, and the next page is the next section. So we're just going to finish this up, and we should be done in hopefully less than 30. All right, example 5, Northeast Airlines determines that the marginal profit, remember marginal profit means that we have a derivative, resulting from the sale of X seats on a jet traveling from Atlanta to Kansas City in hundreds of dollars is given by P prime equals square root of X minus 6. Find the total profit when 60 seats are sold. Okay, so in this case, again, we're going to do the same thing. We're going to set up an integral. We want to find the total profit when 60 seats are sold, so we want to figure out what the profit was from going from 0 seats sold to 60 seats sold of the square root of X minus 6 dx. Okay, remember that the square root of X is the same as X to the 1/2 power. So this is X to the 1/2 power. When we take the antiderivative, it'll make it easier to think of it that way. So when I raise that power by 1, it's X to the 3/2. Dividing now by 3/2 is the same thing as multiplying by the reciprocal 2/3. And then the antiderivative of negative 6 is just negative 6x. And we'll evaluate that from 0 to 60. And what you'll find here, the nice thing is when I plug in the 0 for my second bound, 0 times all that stuff is going to be gone, so it won't even really matter. So we're going to have 2/3 60 to the 3/2 power minus 6 times 60. And then again, if I were to do all that, technically I would subtract plugging in 0 to everything else, but plugging in 0 to X and both of those things is just going to give us 0. So our total profit here is going to be, and that's really what all this gives us here, is this is the profit. Our total profit here is going to be whatever 2/3 times 60 to the 3/2 minus 6 times 60 is. We want to actually get some kind of a decimal approximation here because we want this in terms of money. That's easy to do, and 60 to the 3/2 is not going to be an easy one, so we're going to plug this into a calculator. And after plugging that into a calculator, we end up with negative 50.16. So it looks like if we only sold 60 seats on this flight, we're actually at a loss here. The profit is negative $50.16 overall. Probably have to sell a few more seats on a commercial airline before you can actually start making a profit. But there you go. So that would be how you would find the total profit given a marginal. You just plug it into your integral, 0 to whatever you're trying to find, and you'll have it. All right, that should be plenty enough.